All right. Well, happy Friday, you guys. It is Friday of week 7. So we just have basically 3 more weeks, week 8, week 9, and week 10. And then that will be it. So I hope you guys are doing okay. And we'll take a look at what we've got today. All right. So today we'll wrap up the kind of the final root finding method that we talked about root finding methods on Wednesday, and so we'll we ran out of time before we got to the bisection methods. We'll take a look at that, and then we'll look at taking approximating derivatives and more. So bisection method is a very simple simple way for finding the root. And kind of the disadvantage of bisection method is that it converges slowly. Well, I mean, relatively slowly compared to some of the other methods, but it's also the only one that's kind of guaranteed to work. Okay, in that if you have a continuous function, and if basically you find an interval where the left-hand side is negative and the right-hand side is not, where one side is negative and one side is positive, not necessarily left is negative and right is positive, but just where one side is negative and one side is positive, we know that if the function is continuous, that there has to be a root somewhere in there. Okay, and what we do is we bracket the root. We know that the root has to be somewhere in there, and we iteratively just kind of shrink that bracket, that interval, in half, knowing that the root must lie somewhere inside the interval. Okay, and so basically you start off with some interval, and I've got XL and XR for the X on the left and X on the right, and we know that a root has to be in here if either the left-hand side is negative and the right-hand side is positive, or if the left-hand side is positive and the right-hand side is negative. Okay, and so one way to kind of make sure that that they have different signs is you just take the product. You take the product of f on the left and f on the right, and as long as that product is negative, you know that one side is positive and one side is negative. You don't actually have to evaluate, is if f on the left is negative and f on the right is positive, or if f on the left is positive and if f on the right is negative or something. You can just say, is f on the left times f on the right, is that negative? And that's good enough. Okay, and so if they have opposite signs, then a root has to be somewhere in between the left and the right hand side, assuming that your f is continuous. Okay, and so all we're going to do is we're going to just kind of successively shrink this interval to make sure that until we get the difference between the left and right hand side is smaller than some tolerance level epsilon. Okay, and so so the way this is going to work is you start with you've got the left hand side and the right hand side. Okay, and if the difference between your left and right hand side is less than epsilon, and you can stop. Okay, otherwise what you're going to do is you're going to compute the midpoint. Okay, the midpoint is just the left plus the right divided by 2. If that midpoint happens to equal 0, then you can stop. All right, then you found the root. The midpoint is equal, the root is equal to the midpoint. Okay, but generally this is not going to be the case, and so what you will do is if x on the left times x on the times the midpoint, if you multiply these two together and you get a negative value, then you know that the root has to lie in between the left-hand side and the midpoint, right? You have the left side, the right side, and you have the midpoint. And if this is negative and this is positive, then you know the root has to be in between here, okay? And then so you're going to take the midpoint and set that to the right-hand side, okay? But if this, if the left-hand side and the right midpoint are both negative, then you know that the root has to be between the midpoint and the right-hand side. And so if this, you don't have to evaluate another thing. You can just say, well, if this is not negative, then the midpoint then the midpoint and the right-hand side must contain the interval. And so you're going to take x midpoint and assign that to be the left-hand side of your next interval. Okay, and then you just repeat over and over and over. Okay, and so every iteration, the left-hand side and the right-hand side that you choose will always contain a root, and then this is kind of guaranteed to converge at a root, and basically it reduces the amount of error by a constant factor of 1/2. Okay, and so when you stop, you're going to be within some value epsilon of the root. Okay, so this is kind of the function that we've been taking a look at. We've got log of x minus e to the negative x. All right, and the root is around 1.3. And so here I'm going to just kind of arbitrarily, we just kind of pick two numbers, x on the left to be 1, x on the right to be 2. Okay, and we're going to say the tolerance will be 10 to the negative 8. Right, we evaluate f at x on the left. We evaluate f at x on the right. We have f of L and f right. And we have, is the left-hand side times the right-hand side, is that less than 0? And that comes back true. So we're going to continue on with our algorithm. And so this is what the algorithm looks like. We're going to say while the right-hand side minus the left-hand side is greater than some tolerance level, which is 10 to the negative 8 right now, we're going to run, we're going to run this algorithm. These are the steps of the algorithm. We say, all right, calculate the midpoint. The midpoint, xm, is the left plus the right divided by 2. Evaluate f at the midpoint, okay? F at xm is f at the midpoint. If f at the midpoint is equal to 0, and we're using all equal to be, if it's equal, if they're all equal, because this allows for things that are approximately 0, within kind of the machine tolerance. So if this is equal to 0, then we'll quit out of our loop. Okay, otherwise we'll continue on, and we're going to just check if f on the left times f at the midpoint, if that's less than 0, then we'll take the midpoint and assign it to be the right-hand side of our interval. And if this is not less than 0, then we'll take the midpoint and assign it to be the left-hand side of our interval. Okay. And then we up our iterations and we just continue. And so after 24 iterations, it says the midpoint of our interval, x on the left and x on the right, is going to be 1.3098. That's what we get. Okay. This is what our picture looks like. Okay. So I started off with 1 on the left-hand side and 2 on the right-hand side. Okay. And we know that a root lies somewhere in between 1 and 2, because f at 1 is negative and f at 2 is positive. Okay. And this line delineates negative and positive 0. And so, and the midpoint of the left-hand side, 1 and 2, is 1.5. And if we evaluate f at 1.5, we get a positive value. Okay. And so that means the root has to lie in between the left and the midpoint. Okay. Because the midpoint and the right-hand side are both positive, so we know there's no root there. Okay. We know that there has to be a root on this side. Okay. And then so what we're going to do is we're going to take this and we're going to divide this in half. So halfway between 1 and 1.5 is 1.25. And we're going to evaluate 1.25. And we're going to pick the side so that the endpoints of our interval have different signs. Okay, so when we evaluate 1.25, you get a negative number, and that means we know the root is not going to be over here because the left-hand side and the midpoint are both negative. So we know that the root has to be between the midpoint and the right-hand side, and so we keep the midpoint on the right-hand side, and we continue on. We're going to split this in half. And we eliminate that side. And then we're going to take this and we're going to split it in half. Okay. And we get something close. We get something close to the root, but this is actually still a little bit positive. 1.3125 is still a tiny bit positive. And so, so we're going to continue. We keep this side. This is a little bit positive. This is negative. And we split that in half. And so we're going to eliminate this half. And this is negative and this is still positive. We cut that in half, and we just keep going and going and going. And eventually we'll get to kind of, we'll bracket off the root to be somewhere close here. 1.3098 is where we go, okay? So again, this bisection method, it's pretty good, but it's considered to be, one of the slower algorithms. And so, what a popular method is to use something like bisection method to get you close to the root, okay? So, because if you keep splitting in half, you know that you'll never get, you'll never get your interval totally down to 0 or something. And so, what we often do is we use a bisection method to get you somewhere arbitrarily close. So you say, as long as, maybe you run it enough iterations so that the left-hand side and the right-hand side has a difference of, say, 0.05 or something, a small value that should get you pretty close to the root. And then you can switch over to Newton-Raphson method. And Newton-Raphson method says, you know what, this is going to work well as long as you are kind of arbitrarily close to the root, right? And because Newton-Raphson method, it's a great method, but it can run into issues in searching for a root, especially if your starting point is not that close. It can end up bouncing all over the place. And maybe, I don't know if you've taken a look at your homework yet, but I've intentionally put in some examples in your homework where Newton-Raphson method doesn't converge, or it gets stuck in a cycle or something like that. Okay, so those are that's an idea for finding a root there. Okay, I have a couple slides on the order of convergence, and this is just kind of some high level talk of just some ideas as far as how quickly do the methods converge to find the root. And the idea here is how much does the because how much error are we reducing every time we go to the next iteration, right? So so we're going to say, at the kind of the nth approximation, so basically at the nth iteration, the error between your approximation and the actual root A is, we're going to say is epsilon sub n, okay? A minus, the approximation at time n is going to be epsilon sub n. And we're going to say, there's some order of convergence, okay, order of convergence P, so that if at the next iteration, if the next iteration is, a certain level smaller than kind of the current amount of error raised to some power P, then that's going to be our order of convergence, okay? Larger values of P correspond to, faster values of convergence, okay? I'm not going to get into the math. I'm not going to try to prove or derive any of these things. These are just kind of things to kind of just throw out there and say, these different methods have different rates of convergence. So when we look at something like the bisection method, okay, we're basically taking our interval and we're splitting it in half, okay? We're splitting it in half. And so that means, the next iteration, epsilon at time n plus 1, is going to be half of our current kind of error, for some large, far distant into the future here, okay? And so, so kind of the order of magnitude here, the order of convergence is 1, and so we would say this is, it converges linearly, linear convergence, okay? Under certain conditions, and again, it says it can be shown, and I'm not going to show you, under certain conditions, the Newton-Raphson method has an order of convergence of 2, okay? That is, at time n plus 1, the order, you can take kind of your current error and square it, which shrinks it at an even faster rate. So that we call that quadratic convergence. If you take a look at secant method, its order of convergence is around 1.6, which is something around the golden ratio. Okay, again, just kind of just throwing that out there as a description. All right, let me go ahead and give you your first quiz answer, view quiz answer for today. First view quiz answer is D as in dog. D as in dog is today's first view quiz answer. Okay. Our do we have any questions here? Is this all good? All right, let's take a look at, sorry, give me a moment here. Okay, let's take a look at approximating derivatives. So, so later today, we'll look at some optimization methods that use derivatives, and so it'll be useful to be able to calculate derivatives. And you know, we learned the Newton-Raphson method for root finding, and that uses derivatives here. Okay, so we say, you know, the next value x of n plus at time n plus 1 is your current value x at time n minus f of x n divided by f prime of x n. Okay, and you know, and we run this until, you know, f of x is close enough to 0. Okay, but this requires us to evaluate the derivative f prime. Okay, and so well, in our example, when we had our function as log of x minus e to the negative x, finding the derivative is pretty straightforward and simple. All we have to do is take derivative of log of x and we get 1 over x. Derivative e to the negative x is e to the negative x times negative 1, and so this becomes plus this. So taking the derivative was a straightforward process, not too bad. Okay, but there are you know, some instances where it can get hard to take the derivative here. Okay, but anyway, let me just show you. So what we did is we just wrote like f is log of x minus e to the negative x, and then we said f prime is going to be 1 over x plus e to the negative x. And if we evaluate f at 5, we get 1.6, and if we evaluate f prime at 5, we get 0.2067. Okay, so the derivative at 5 is 0.2067. Okay, and so here's the graph of f at x equal to 5, and at x equal to 5, this is the tangent line. Okay, the slope of this tangent line is 0.206. It looks a little bit a lot steeper than that, just because the scale on the y-axis, vertical axis, is greatly different from the scale on the x-axis. Okay, but this is the tangent line at f equal to at x equal to 5. Okay, so this is the tangent line here. Okay, what we'll take a look at here is approximating the derivative numerically. All right, so if for whatever reason we had a hard time finding the analytic derivative analytically, we can approximate it numerically. All right, and so the way we're going to approximate the derivative is we're going to kind of just use the definition of the derivative. So, you know, when you took calculus, the definition of the derivative is, you know, the limit as h goes to 0 of f of a plus h minus f of a divided by h, right? And we just say as h goes to 0, this is going to be the derivative f prime at a. Okay, so we're just, you know, what's the how much does the function change going from a to a plus h? And we're going to take the, you know, the difference vertically and divide it by the difference horizontally as h shrinks smaller and smaller. Okay, and basically all we're going to do is we're just going to add some small constant value h here. Okay, and so here I've written a function that's going to take the get an approximate value for the derivative. So here h is 10 to the negative 6. Okay, so yeah, 10 to the negative 6. I'm going to evaluate f at x, which will be log of x minus e to the negative x. And then we're going to evaluate f at x plus h. Okay, f at x and h is going to be log of x plus h minus e to the negative x plus h. Right, and then we say, well, how much is the difference between f of x at x plus h minus f of x? What's that difference? We're going to take that difference and divide by h. And so So I plug 5 into this function, and it says, all right, well, if I plug 5 in, I'm going to calculate f of x, and we're going to do 5 plus 10 to the negative 6. And then we're going to calculate this, and then we take the difference and we divide by h. And it says, the slope that we've calculated using that approximation is 0.2067379236669. Okay. Now, if I compare that to the actual analytic derivative, okay, the analytic derivative we found back here is 1 over x plus e to the negative x. Okay. If I plug in 5 there, I get 0.20673794699. So we can see that this approximation right here and the actual analytic derivative, matches up to around seven places after the decimal, 0.2067379, and then the digit after that is a 2. Here I got 0.2067379, and the digit after that is a 4. Okay, so we're accurate up to 7 places. And it's only until we get to the 8th place that we're off by a little bit. So I would say this gives us a pretty good approximation. Our approximation is pretty close to the true value. And we achieved that. We didn't bother calculating the derivative analytically. We just said, take this function, add on a small little h value to x, and take the difference and divide by h. So in this one, I added a positive h to x, but you might wonder, well, can I just do this on the left-hand side? What if h is a negative value? Okay, what if h is a negative value? So if I do the same thing, okay, but this time using a negative value for h, okay, so I'm going to do f of x, and then we're going to do f of x plus h, but this time h is a negative value, negative 10 to the negative 6. Okay, what value do I get there? Okay, well, the answer is you get something very similar, but it's going to be a little bit off. Okay, so this is the quote true value. All right, and I say quote true value because everything in floating point numbers is an approximation anyway. But here we get 0.20673794699. Okay, if I take the left-hand side, the left-hand approximation to the derivative, okay, again, we're accurate up to 7 decimal places, and then the 8th decimal place is a 7 rather than a 4, okay? And then if I take the approximation on the right-hand side, we're accurate up to 7 decimal places, and then the 8th decimal place is a 2, okay? So the left-hand side is a little tiny bit too big. The right-hand side is a tiny bit too small, okay? And that's because there's a little bit of curvature in the function, okay? And whenever you have curvature, the left-hand side or right-hand side will differ slightly. One is going to be a little bit too big. The other one's going to be a little bit too small. And so what we can do is we can just, we can take a look at both the left and the right-hand side and kind of take the, some value in between, right? So this is an exaggerated picture. Okay, so here, this red line, the red dashed line, is the true tangent line, okay? This orange line runs through the 0.5 and is basically a secant line where, one of the points is in the middle and the other point is over on the left side, okay? And we can see because the slope curves like this, on the left-hand side, we're just a tiny bit too steep. And as it curves down over here, okay, on the right-hand side, okay, it runs through this point right in the middle, and then it runs through this point over here. On the right-hand side, we're a little bit too shallow, okay? And again, this is grossly exaggerated. Okay, but the left-hand side is just a tiny bit too steep. The right-hand side is a tiny bit too shallow. So what we can do, okay, so if I add a negative value, I get too steep. Right-hand side, I get something too shallow. What we can do is we can take both the left-hand side and the right-hand side and average those, basically, okay? So here I'm going to do the kind of my balanced approximation. My balanced approximation is going to take some value h, 10 to the negative 6. We're going to do x plus h, and then we're going to also evaluate at x minus h. So we're going to say f of x plus h and f of x minus h. And we're going to take the difference between, the plus side and the minus side. What's that difference? And we're going to divide by 2h, just because, we start at the midpoint. We want h this way, and we want h this way. And so we're going to take the difference between these two planes. The horizontal distance is 2h, and the vertical distance will be, f of x plus h minus f of x minus h. So we're going to take that. Okay. And so when we do that, this is going to be my balanced approximation between the left and the right-hand side adjustments. And we are now accurate to 10 decimal places after 10 places after the decimal. 0.20673794694 versus 20673794699. So we're getting very, 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 very close values. Okay. And this is just, and again, this is an approximation. We didn't actually calculate the derivative analytically. All we did was we just plugged in two values into our function, took the difference, and divided it by 2h. So we can generalize our approximation by making a function, or one of the arguments is going to be a function itself. Okay, so we're going to say the derivative of f is going to be, we're going to take the f and we'll do x and h, some arbitrary constant here. The left-hand side will be x minus h. The right-hand side will be x plus h. We evaluate the function on the right-hand side, evaluate the function on the left-hand side, take that difference, and we're going to divide by 2 times h. Okay. And so we just put in some arbitrary function that we put in. Okay. So we can see, here's the thing that we did earlier with f. And if I plug in f into here, what's the derivative of f at 5? Okay, I get my approximation here. Here's just a very simple function. I'm going to say f2 is the function x squared. Okay, x squared. That's about as easy as it gets. So the derivative of x squared is just 2x, right? And so we can say, well, what's the derivative of x squared at 5? And it comes back and it comes back and it says it's 10. If you say digits equals 12 and you ask for additional digits, you see, okay, now you start to see the results of the approximation. It's not exactly 10. It's pretty close to 10. It's 10.0000000014. Okay, so we're off by a very small number, but I'd say this is a pretty good approximation to the actual value here. Okay, and so we can use that to approximate derivatives, and the computer, all it sees, this is just a function. Okay, you plug in a number and it spits a value out. Okay, you plug in a number and it spits a value out. The computer doesn't really know that this was not found analytically. Okay, the computer has no idea. It's just to it, you have a function, it just takes a number in and it gives a number out. Okay, and so it doesn't care whether the insides of the function were found analytically or found using some approximation method. All it sees is a thing that puts a number in, it gives us a number out. Okay. One thing we have to be careful of is we have to be mindful that we're not dealing with real numbers on the computer. The computer is always dealing with floating point numbers. And when you have floating point numbers, you're always dealing with approximations, and you only have a finite amount of precision. Okay. So for the function x squared at 5 evaluates to 25. Okay. And when you have a number like 25, that number is between, if you think of powers of 2, that number is between 16 and 32, okay? Between 2 to the 4 and 2 to the 5, which means basically you're going to be using the amount of precision that you can have, okay, is going to be your machine epsilon times 2 to the 5th. So it's going to be a little bit off, okay? So I don't know if you've done taken a look at your homework this week at all, but basically your machine epsilon, which is the amount you can add to 1 and the computer can differentiate, that's going to be different than the amount you can add to the number 2, which is different than the amount you can add to the number 4, which is different from the amount you can add to the number 8. Okay, as your numbers get bigger in orders of power of 2, the amount that the computer can differentiate between one number and the next, basically doubles in size. And so for something on the when we're dealing with numbers like on 25, how much precision can we expect? It's not actually helpful to just say, well, you know what, I want to make my h to be as small as possible, right? So I think in most of my examples, I've been just adding 10 to the negative 6. But you can say, well, you know what, maybe I can get a better approximation of the derivative by adding 10 to the negative 7 or 10 to the negative 8 or 10 to the negative 10. Why don't I just pick an h that's as small as possible? Well, you're not going to get better results necessarily. Okay, so if I add 10 to the negative 5, remember the true derivative of x squared at 5 is 10, and so we want to see which values get us closest to 10. Adding on 10 to the negative 5 gives me a value close to 10. Basically, the last 6 digits are a little bit off. Okay, adding 10 to the negative 6 also gets me very close to 10. The last 6 digits are off. Adding 10 to the negative 7, in this case, actually the last 7 digits are off. And same with 10 to the negative 8, the last 7 digits are off. Okay. As I add smaller and smaller numbers, you'll notice the amount that I'm off by actually gets bigger and bigger. When I'm adding 10 to the negative 15, this isn't even 10 anymore, okay? It's 8.88, okay? And if I try adding 10 to the negative 16, it just tells me that the derivative is 0, okay? And so what's happening here is that when you evaluate x squared at 5, you get 25. And at 25, 1 times 10 to the negative 16 is smaller than my machine epsilon. I cannot add 10 to the negative 16 to 25 and get a number that the computer recognizes different than 25. And so what it's going to see is just 25 minus 25, and it's going to see no difference, and it's going to give us a slope of 0. And so, so you have to kind of keep in mind just the limitations of dealing with floating point numbers. And you can't just say, I want to pick the smallest h that I can to get kind of the most precise answer for derivative approximation. Okay. And for this example, we've been using 10 to the negative 6, but also as your numbers get bigger and bigger, you might, let's say you're adding numbers like a billion, okay, 1 billion and 2 billion or something like that. 10 to the negative 6 might be reaching the limits of the computer precision, okay? The computer might not be able to keep track of 10 to the negative 6. So when you're dealing with numbers that are on the orders of billions, you might want to add an h of 1 or an h of 2 or something like that, not an h of 10 to the minus 6 or 10 to the minus 7. I think at a billion, 10 to the minus 7 won't even differentiate between, I don't know, maybe it's 10 to the minus 8 at 1 billion, I'm not sure. Okay, so you got to kind of keep in mind what your floating point limits are, just because you don't have infinite precision here. We're not dealing with real numbers. Okay, yeah, so this just to say accuracy drops dramatically as we get really small h's adding. All right, let me give you another quiz answer. Second quiz answer is A. A is an apple. A is an apple. Okay, And the last bit that I want to touch on today will be derivative-based numeric optimization. Okay, and so we've seen a lot of root finding methods, and we can use those root finding methods to help us find optimums. Okay, optimization is all about finding minimums and maximums. Okay, we want to find a local min or a local max, and that's what optimization is all about. And our root finding methods can be used for optimization. Okay. You can take an entire course on optimization and different kind of methods and whatnot. And it's all about finding local mins and local maxes. We're going to just kind of take a very, very, very shallow introduction right now. Okay. And we'll take a look at a couple methods. A lot of algorithms are used to find a local minimum of some function f. If you need to find a local maximum, then all you have to do is you apply the minimization algorithm on negative f of x, all right? And so if you find the minimum of negative f of x, that's going to equal the maximum of f of x, right? It's the same location for the max of f of x. Okay, but anyway, let's just talk about derivative-based numeric optimization. And all we're going to do is we're going to just apply a root finding method to the derivative of a function, okay? So to find the local min or local maximum of some function f, we just find the roots of the derivative of f. And so when you find where the derivative is equal to 0, that is, you find the roots of f prime, the roots of the derivative will provide critical points, and those critical points will correspond to local min, local max, maybe a saddle point, but overall you find the critical points of the function by finding where the derivative is equal to 0. Okay, so you find the derivative of f, apply any of the root finding methods that we learned on Wednesday or today. Okay, and you find the roots, and then you evaluate those critical points. So probably one of the most common method is the Newton-Raphson method. Newton-Raphson method is very popular for root finding, and it's very popular for optimization. Okay, so basically you're just going to find the roots of f prime. Okay, if you find the roots of f prime, that will give you the critical points of f, which will correspond to local minimums and local maximums. Okay, and so you have to start at some arbitrary starting location that is expected to be close enough to the local min or local max. Okay, and again, this is a little bit tricky, but you could use some kind of method to help you get close to the local min or local max. And then all you do is you iteratively find the next value by saying x at time n plus 1 is going to be x at time n minus f prime of x divided by f double prime of x. Okay, and so if this was Newton-Raphson method. Newton-Raphson method, we said x at time n plus 1 is going to be x at time n minus f of x divided by f prime of x. Now we're trying to find the roots of f prime, so it's going to be x at time n plus 1 is going to be x of n minus f prime of x divided by f double prime of x. Okay, because we're just trying to find the roots of f prime of x. And we're going to stop when this part, f prime of x, is close enough to 0. So when f prime of x is less than some epsilon value, then we'll stop. Okay. So the only the conditions here is that f needs to be twice differentiable. You need a function that you can differentiate twice, and if f double prime is this part is not allowed to be 0 for any of the xn's that you check. Okay, it's allowed to be 0. It's allowed to be 0. It can cross 0, it can go from negative to positive and things like that. That's fine. It's just inside your sequence, depending on your starting point, xn, it's f double prime at xn is not allowed to be 0. Otherwise, you're going to run into a problem. Okay, so as long as your starting sequence doesn't lead to a situation where f double prime is equal to 0, you're going to be in good shape. Okay, and so this is just a very, very simple example. We just said, here's a sum function 0.25x to the fourth, 0.5x squared. The first derivative is going to be x cubed minus x, and the second derivative will be 3x squared minus 1. So I found these analytically. But again, if you can't find something analytically, you can just evaluate it, take an approximation numerically. Okay, you can take the numeric derivative approximation, and that will also work just fine. All right, and so we're going to find the roots of f prime. So we're going to just run the algorithm, take, say, the next, the value at the next iteration is going to be our current value minus f prime at the current value divided by f double prime at the current value. All right, so here's some function, and we want to find local mins and local maxes. And I'm just going to choose some arbitrary starting points. So I think my first, so my f prime is going to be x cubed minus x. F double prime is 3x squared minus 1. And I'm going to just start off at 2.1. And then we'll say the next iteration will be my kind of current value minus f prime at the current divided by f double prime at the current value, x old. And then we'll just arbitrarily set some tolerance to be 1 times e to the negative 6. And all we're going to do is we're going to take the current value, kind of the newest value, make that the old one. We're going to take the x old minus f at the old, f prime at x old minus divided by f double prime at x old. Okay, and that's going to be the new value. And we just throw that in a while loop, and this is going to just run iteratively. Okay, and we'll stop when the difference between x new and x old, when that difference is less than 10 to the negative 6, we'll stop. And it runs, and the value it evaluates to is, it says 1. Okay, and looking at our plot, oh yeah, that indeed looks like a local min. If I start off at some other location, here I started off at 0.9. Okay, it runs, same code here, and it stops when we get to 1.000, almost exactly 1. It's a little off by a tiny bit. Okay, so it says, all right, this is going to be your local min. Here I start off some location at 0.1. So if I start off at 0.1 and I say try to find a critical point where the derivative is equal to 0, okay, find a root of the derivative. This evaluates, and we get negative 9 times 10 to the negative 24. So this is pretty much something very close to 0. It evaluates to a very small number, 10 to the negative 24. And so that corresponds to kind of this local max right here. And just for funsies, I started off at just some arbitrary location, negative 10, and I let it run. And then it found the local min of negative 1 here. Okay, so this is pretty much the Newton-Raphson method, except instead of doing f divided by f prime, I'm doing f prime divided by f double prime. Okay, and that will lead to roots of the derivative, and roots of the derivative will correspond to local mins and local maxes, or saddle points. You know, they're basically just critical points of the function there. All right. Do we have any questions there? Sounds okay as far as optimization methods. And so on Monday, what we'll do is we'll take a look at a few more optimization methods. We'll look at the golden section search, and we'll also look at coordinate descent. Sorry, my brain got stuck for a second. All right, let me give you your last quiz answer for today. Last quiz answer is E as an elephant. E as an elephant will be your last view quiz answer. And that should be that. Have a good weekend, and we will see you guys on Monday.
Thank you. Hope you have a good weekend.
Thank you.